Welcome to the lecture number 49 of Fuzzy Sets, Logic and Systems and Applications. In this lecture, we will discuss fuzzy rules and fuzzy reasoning. So here, when we talk of fuzzy rules are always in the form of if the linguistic variable is some linguistic value, then again the linguistic variable as the output is some linguistic value. So the fuzzy rule has a particular syntax. The syntax is like this, like if we have any fuzzy rule will look like this. Fuzzy rule will have if part and then part. So any fuzzy rule will have if and then both the words. And please understand that any fuzzy system will have a set of fuzzy rules. Without a set of fuzzy rules, there can be no fuzzy system. Or in other words, there can never exist any fuzzy system without a set of fuzzy rules. So a fuzzy if then rule, like if x is A, then y is B, and we already know that if x is A is called as antecedent or premise, and in this rule the then y is B is called as consequence or conclusion part. So any fuzzy rule has two parts. The first part is the premise part or the antecedent part, and the second part is the conclusion part or the consequence part. So this fuzzy rule in this form, the fuzzy rule if x is A then y is B can be written as A forward arrow B. So this means we have A and then B. This means that if a particular fuzzy variable or the linguistic variable belongs then to a particular fuzzy region, that is the linguistic value that is represented by a fuzzy set, then what is B? What is the output? What is the linguistic value out of it? So this is how it is written. So A forward arrow B is also written for a particular fuzzy rule. So there are two ways to interpret a fuzzy if then rule. First is A coupled with B, and then the second one is A entails B. So here are the two ways, as I mentioned: A coupled with B, A entails B. So this suggests that a fuzzy if then rule can be defined as a fuzzy relation here, a fuzzy relation. And we already know that how we get a fuzzy relation from fuzzy sets. So a if we have a set of fuzzy sets, like if we have two fuzzy sets A and B, and if we are interested in finding the relation fuzzy set, so relation fuzzy set will be nothing but the Cartesian product of these two fuzzy sets. So, and then of course, the universe of discourse of this fuzzy relation set will be the, the cross product of the universe of discourse of the first fuzzy set and the second fuzzy set. So, uh, for any continuous fuzzy sets A and B, if we are interested in the relation fuzzy set, say R, so this R can be written as the fuzzy relation set can be written as A forward arrow, that means the A coupled with B, and we have this will be equal to A cross B, and we can always write the same with this expression we have already done in the previous lectures. So integral sign and then the universe of discourse of it will be x cross y, and then we have mu r of xy oblique x comma y, and then for every x comma y will be belonging into the universe of discourse of x, capital X cross capital Y. So this is for the continuous one, for the continuous fuzzy relation set. Similarly, if we have A and B both are discrete fuzzy sets, then of course the fuzzy relation set will be the discrete set, discrete fuzzy set. So here we have already done this in the previous lectures, so I'm not going into this again. So here the fuzzy relation set fuzzy, in other words I can say the discrete fuzzy relation set, discrete fuzzy relation set R. So that is how we get a fuzzy relation set out of A, fuzzy set A and fuzzy set B by taking the cross product of it, or I would say the Cartesian product of it. So here let us now go one by one. So fuzzy rule interpretation when we do with by using A coupled with B. So when we interpret A arrow B, arrow forward, A forward arrow B, we interpret by A coupled with B, then it can be interpreted by a fuzzy relation R, as I mentioned here. R we know how did we get, you see here. So the same will involve here. When we say A coupled with B will involve the T norm, or S conorm. So here also we have T norm in the discrete version of it. So we can simply write the fuzzy relation set by R, and then we use T norm when we interpret the fuzzy rule by A coupled with B. And since we are using T norm here, and we know that we have 4 types of T norms normally available. So we can use here the same as A coupled with B for the relation fuzzy set using minimum T norm operator. So we know that the first and the most basic T norm operator is the minimum. So we take the minimum. The first kind of T norm is minimum. Then the second kind of T norm here is the algebraic product. So we can use the algebraic product here as one of the T norms or S conorms. We already know that T norm is also called as S conorm, and similarly S norm is also called as T conorms. So the third one is when The relation fuzzy set can be obtained by using the bounded product as the t-norm operator. Similarly, the fourth one here is the drastic product as the t-norm operator. So here we can use any of the four t-norm operators to get the fuzzy relation set for either discrete fuzzy sets or the continuous fuzzy sets, and both the versions are here as mentioned.
Now, fuzzy rule interpretation as A entails B here. So we have, if A forward arrow B is interpreted as A entails B, then it can be defined by the following four different forms. So first form here is the material implication, and the second form is propositional calculus. The third form is extended propositional calculus. The fourth form is the generalization of modus ponens. So material implication is represented by R suffix mi is equal to A entails B is equal to negation A union B. Propositional calculus is represented by R suffix PC is equal to A entails B is equal to negation of A union of A intersection B. Similarly, we have extended propositional calculus, and here this is represented by R EPC which is equal to A entails B is equal to the union of negation of A intersection negation of B and B. The fourth one is the generalization of modus ponens represented by capital R GMP is equal to A entails B is equal to A. Then we have the tilde less than B. So A entails B here represents the fuzzy relation R. So let us go one by one and see what is the material implication. So material implication is defined, as I have already mentioned, by RMI, which is equal to A entails B is equal to the negation of A union B. So if we have a continuous fuzzy set, let's say, the RMI will be like this. And if we have a discrete fuzzy set, the RMIB for discrete fuzzy set will be expressed by this expression. Similarly, the continuous one will be this. So this is also called the Jades arithmetic rule. This is very important to note that the Jades arithmetic rule, which follows the negation of A union B by using the bounded sum operator for union. Now, the propositional calculus, where the R, the fuzzy relation set R, PC, where we have A entails B, is the union of negation of A and the intersection of A and B. This. So when we apply this to continuous fuzzy sets A and B, we are going to get this expression. Similarly, for discrete fuzzy sets, when we apply the propositional calculus, we get a relation on propositional calculus RPC by this expression. And this is called the Jades max-min rule. This is very important to note, which follows the negation A union of A intersection B by using min for intersection and max for union. So wherever we have the min, we use the min, we use the intersection, and for max, we use union. Now, the third one, that is extended propositional calculus. So here we have RPC, and RPC A entails B is equal to the union of negation of A intersection negation of B and B. So when we apply this for continuous fuzzy sets A and B, the relation fuzzy set, which is REPC, the relation fuzzy set for extended propositional calculus, will become REPC, and this is found by this expression for continuous fuzzy sets. Similarly, for discrete fuzzy sets, we get like this. The RPC we get like this. And this is called the Boolean fuzzy implication. This is called the Boolean fuzzy implication using max for U. Means wherever we have max, wherever we have union, we use max. So then comes the fourth one here, the generalization of modus ponens, and the fuzzy relation set that comes out of this is represented by RGMP, and this is equal to A entails B, A, which is nothing but A, tilde less than B, and this is represented by RGMP, and here this is for the continuous fuzzy set, where we have the RGMP of xy oblique xy here. So RGMP is computed simply by this expression here. And if we have a discrete fuzzy sets A and B, then the fuzzy relation set, that is RGMP, we can get here at the summation over x cross y mu RGMP, and then again this mu RGMP is computed by this expression. This is called as the Gogun's fuzzy implication, which follows A tilde less than B by using the algebraic product for T-norm operator. So this way we can very easily compute the fuzzy rule interpretation as A entails B for fuzzy sets A and B to get the fuzzy relation set. Now let us take an example here to understand this fuzzy rule interpretation as A entails B. So for this example, the S high and P high, where the universe of discourse for S high is this, for S is this, and for universe of discourse for P here is 1, 2, 3. So we have two discrete fuzzy sets here, S high and P high, represented by the two fuzzy expressions, two fuzzy sets. Now, since we have S high and P high, so we can now further go ahead and get the RMI. So this is RMI, the material implication. So this is very simple here. When we use RMI, so we use for RMI, we use this negation of S high union P high. here. And this we already know as to how we get here. So if we want to compute this, the RMI, simply for computing the membership values of RMI, we use the mu S high here, mu S high, this one, and mu P high. So both the membership values we take and then we compute the membership value of RMI. So R is the relation fuzzy set for material implication. So this way we get this relation matrix, this fuzzy relation matrix, and finally when we compute, we are going to get the RMI here like this. So we can write here the fuzzy relation matrix RMI, and MI is nothing but the material implication. We can write here with material implication. Similarly, we used the same two matrices, we use same fuzzy sets, S high and P high, both are discrete. And when we use propositional calculus, so for propositional calculus, we use the negation of S high union S high intersection P high. So when we do that here, we get the fuzzy relation matrix, fuzzy relation matrix RPC. So this is we are going to get after using the propositional calculus. The expression is here. So we know as to how we are going to compute. And then finally, we are going to get RPC, which is the fuzzy relation matrix based on the propositional calculus. Now, the third one is based on extended composition. So for computing the extended propositional calculus, we take basically the union of negation of S high intersection negation of P high and P high here. So when we do that, we used this expression, and finally we are getting REPC. Here again, there is nothing but the fuzzy relation matrix REPC. EPC is nothing but the extended propositional calculus. Now the fourth one is generalization of modus ponens. When we use this, so RGMP we get by simply taking the S high tilde less than P high. You can see here. So since we have S high and P high, so when we find this mu RGMP of SP, please understand this S here is nothing but it is the generic variable, and P also is the generic variable here. So this way mu RGMP we can compute here with this expression, with this condition here. And when we use this, we are going to get the fuzzy relation matrix, RGMP. So this way we get the fuzzy rule interpretation as A entails B. So that's how we have been able to manage to get various kinds of fuzzy relation set in the form of fuzzy relation matrix. And with this, I would like to stop here, and in the next lecture, we'll study the fuzzy reasoning. Thank you.